the second presentation, titled A Novel Solution for Live Load Continuity in Multi-Span FRP Composite Tap Girder Bridges, given by Bill Davids. Dr. Davids is a professor and chair of civil and environmental engineering at the University of Maine, where he teaches classes in structural design, structural analysis, and numerical methods. He was a bridge engineer for 40 years prior to entering academia in 1998. Bill has directed research in bridge engineering, inflatable structures, composite materials for infrastructure applications, and the mechanics of solid and engineered wood. He has authored and co-authored over 70 articles in peer-reviewed journals, co-holds 4 patents, and has developed several finite element analysis packages used in industry and academia. Bill has a PhD in civil engineering from the University of Washington, BS and MS degrees in civil engineering from the University of Maine, and is a licensed professional engineer. Unfortunately, Bill is unable to be here in person today, so he has pre-recorded his presentation.
Okay, thanks everybody for coming. I apologize for not being there and connecting with all of you this year, but hopefully this will fill the gap reasonably well. I'd like to talk today about how we are developing live load continuity in multi-span FRP composite tub girder bridges. Before we dive in, I want to go through the anatomy of a CT girder bridge and also a little bit of background briefly on the work we've done to date and where that's positioned us. So the CT girder bridge is an FRP composite tub girder. It's got a concrete deck and an FRP girder with a carbon fiber bottom flange, E-glass webs, and we've got some shear connectors in there that tie the deck to the girders. It's shown schematically on the upper left. Notice the girders are not filled with concrete, they are hollow. It is the FRP doing all the work. The picture on the right is showing you the Hamden Gristmill Bridge. This is the first bridge of this type constructed back in 2021. And it's a substitute for a steel or concrete girder, and it's currently capable of simple span it's currently used for simple span construction, maybe up to 100 feet or so. The Hamden Gristmill Bridge is a 75-foot span. That's the longest one that's been done to date. Now, we've done a lot of work, testing and simulation to verify its performance. We've done laboratory testing of girder strength, shown with a 4-point bend test in the photo on the upper left. Some results of the most recent test of that is shown on the right. We're greatly exceeding the required strength because of the design guidelines that we use for the girder, but performance is very good and as expected. We've done a lot of modeling and simulation that is driving design tool development. And this is really necessary because with FRP, there are other limit states that must be checked. There are no closed form solutions. We really have to dig in and do some more advanced analysis sometimes, but we have done a lot of homework to take that off the plate of the design engineer. We've done a lot of field live load testing over a span of 4 years, 2 bridges, each of which has been tested twice. We placed very large live loads on these bridges. We've quantified distribution of live load girder moments and shears, and this has allowed us to develop girder-specific moment distribution factors that can be used in design as well. And more recently, we completed full-scale girder fatigue testing. This was a really valuable test. We had 2 38-foot long girders that were nominally identical to those used in the CT girder bridge in Westerly, Rhode Island. It was completed a few years ago. One of those girders was tested to failure to determine its virgin strength. The second girder was subjected to 3 million cycles of factored AASHTO1 fatigue loading to look at the loss in capacity or the damage that had occurred over that. We did a really detailed analysis of the fatigue data, and that actually allowed us to predict how much truck loading these CT girders can take. And we ended up with a capacity of almost 4,000 trucks per day per lane for 100 years, which is a very high truck volume. So the fatigue performance of these has been demonstrated in the laboratory to be very good. All of this has led to the point where we published about 6 journal articles, and we've got this information out there in the literature. And we're working now with the AASHTO Committee on Bridges and Structures, actually the subcommittee on special structures, to develop a guide specification for the design of composite tub girders for highway bridges. This work has been presented both this summer and the summer before at the annual AASHTO meeting. And this is going to enhance technology acceptance. We've got, clear design methods that address the critical limit states and are going to be relatively straightforward for a practicing bridge engineer to understand and apply. Now, this brings us to the main topic today. Right now, two bridges in Old Town, Maine, just a few miles north of where we're sitting right now, are being replaced with CT girders. This is over the Stillwater River. It's on Stillwater Avenue. It's a fairly high traffic volume road, about 16,000 vehicles per day. And the bridges that are being replaced are two severely deteriorated steel girder bridges. You can see the photo taken a few years ago showing one of those. You can see a lot of corrosion. And I think that is probably the rustiest water main I've ever seen in my life. And it's got a big sag in it too. There are actually two bridges on site. They're separated by an island in the middle of the river, or close to the middle. The first bridge is two 75-foot spans, and the second bridge has three 95-foot spans. If we're going to use a CT girder here, which we are, that requires some advancements. These are longer spans than all prior structures. We're pushing the limits there. And we also want to build this, more importantly, using a multi-span continuous structure, continuous for live load. This has never, as far as I know, been done with an FRP girder bridge. So the concept we developed for this is on the surface pretty straightforward. Conceptually, I'm showing an elevation view of a two-span continuous CT girder bridge here, where the girders are in green, the concrete is in gray, and we're filling part of the length of the CT girder with concrete over the piers and at the abutments if we're doing an integral abutment bridge, which we are with Stillwater Avenue. And we add additional negative moment reinforcing in the deck to carry the tensile stresses due to negative bending there. It's important to note those girders are discontinuous. They're dropped in as simple spans on individual bearings. And at the pier and at the abutment, it's a pure reinforced concrete section carrying the moment. That we know how to design. That's straightforward. However, a big question is, how do we transfer the flexural stress from the CT girder to that reinforced concrete section at the pier and the abutments? That's the question we have to answer. This is going to increase design efficiency a lot. It's going to reduce live load deflections and reduce bending moments for a given span length when compared to a simple span. It's routine construction for conventional precast concrete girder bridges. But there, it's straightforward because you're transferring stresses from concrete to concrete. Here again, we have to transfer it from FRP to concrete, and we have to be very sure we're doing that reliably. So to achieve that, shown it schematically here on the left, this is a section of a CT girder in elevation. You can see the centerline pier. That's where you have a pure reinforced concrete section with a tension compression couple. And we're filling a length L sub S on the interior of the girder with concrete. And the concept is to use the same stress transfer mechanism that we use to transfer shear from the top flange of the girder to the deck, which we have assessed extensively, demonstrated it possesses. We know the strength of that connection. We know it's got good fatigue resistance. Can we do the same thing here with the concrete infill? So what we're actually doing is we're infusing ridges on the interior of the girder surface in the region of that concrete infill. This is shown in the photo on the right. This is actually a test specimen that we're going to discuss in more detail in a moment. You can see it's two discontinuous sections of CT girder that are being brought together, separated by a few inches. That would represent those few inches of separation would be at the center line of the pier. And you can see those ridges on the bottom flange and on the web. You can also see the ridges on the top of the top flange where the concrete deck will be cast. The ridges have the same overall dimension, same geometry, magnitude, and wavelength. And you can see the bulkheads in there. This is formed up and ready for a concrete pour. The bulkhead would be where that concrete infill stops. So to assess this, we wanted to tackle this as practically and realistically as possible. So what we did is we took the Westerly, Rhode Island girder spacing and cross-section of the roadway. We modified the girder cross-section a little bit. We gave it a wider bottom flange, and that bottom flange width is important because we're transferring via shear, aggregate interlock and shear on that interface to get compression from the girder flange into the concrete. So we made the width of that similar to what we will have on Stillwater Avenue. And we designed a two-span, 100-foot long continuous bridge. In other words, two 50-foot spans, or that's 2/3 scale for the two 75-foot span Stillwater Avenue bridge. So it's not full scale, but it is large. And it's as large as we could make and still manage in our lab. And we calculated that length of splice based on what we know we can transfer across that ridged interface based on our prior work, where we look at that when we're attaching the deck to the girder. And it's a first principles equation where the moment is simply divided by the stress transferred across that interface and the internal lever arm for bending. And it's a little bit more complicated than this. It's an iterative design process because as we infill different lengths of girder, the moments change because you change the flexural rigidity of the continuous structure. But that's okay. We can work through that. And you can see we calculated a length of 3.75 feet. That is, I think it's 7.5% of the 50-foot span. And that's so it's not a large length that we infill. It's actually pretty short. We also added excess deck flexural reinforcement. So we've got to have tension steel in the deck to carry that negative moment across that pier. We added a little extra for extra moment capacity to try to drive the failure to occur at that ridged shear friction connection. And as you'll see, we were partially successful with that, and in a good way. So we fabricated the specimen that was actually made by AIT Bridges. They made this for us and cast all the concrete in their facility in Winterport. It was brought up to the University of Maine's lab. And here's a picture of the specimen image as it was tested in our lab. So it's a 22-foot span, 6.7 meters. You can see the concrete infill is shown there. The hollow sections of the girder don't have any. It was tested upside down. So the deck was placed on the bottom so that when we push down with an actuator, we put tension in the deck and compression on the girder flange. So it mimics what happens in the real bridge when the girder's right side up. With 2 points of load application, you can see through those W8x67s that mimic the individual bearings that are used in a real bridge. Remember, it's we drop in girders on individual bearings and then concrete is poured. And that span length of 22 feet was not arbitrary. That was chosen specifically so that we ensured the correct ratio of moment to shear at the splice. So when we produce MU, the factored moment, we also, with our applied load, we also produce V sub U at the splice because we also have to carry shear as well with the splice. And we first subjected it to 500,000 AASHTO fatigue 2 load cycles prior to driving it to failure. And we don't expect, there won't be any fatigue issues with this. We've assessed this shear friction connection in fatigue extensively in the past, and it's not a fatigue critical detail. We just wanted to settle the specimen and make sure there wasn't anything going on unexpected. So our instrumentation was extensive. I'm not going to go through results of all the strain gauging we put on here and all the instrumentation, but we instrumented at centerline pier section A, we instrumented at 2 sections B and D within the splice, and then C, we instrumented the bare girder as well. And you can see we had a lot of strain gauges on the girder. We instrumented the compression reinforcing within the infill region at sections A, B, and D where it existed. We also instrumented the tension reinforcing in the slab, many of the rebar there. So there's a lot of redundancy as well. We instrumented the same sections on both sides of the splice, and it's a symmetric section. So if we lost a gauge, we'd still have data at that location, et cetera. And I'm going to give you right off the bat, what happened when we loaded this. So this is the plot of actuator load versus midspan displacement of the specimen. And we are cycling load from 50%. We went up to 50% of a service load a few times. We went up to the full service load a few times. And then we drove this thing to failure. And you can see that there are 3 peaks on this curve. We get a first failure at 27, 28 millimeters of displacement, a little over an inch, go another, 7 or 8 millimeters, you get another failure. And then you can see out there at 47 millimeters or close to 2 inches, the true peak load was reached. And that was the final failure. At that point, the specimen was done. And the first failure load exceeded the factored design load by 50%. In other words, this was over-designed by 50%. And we'll talk about why that was in a moment. But that's really good news. It performed a lot better than we'd expected it to perform. I'm going to show you a quick video. This is the failure test. So here's the specimen upside down in the load frame. You can see it's got the concrete diaphragm at what would be midspan, which it will have in the real world as well. And you can see that it's being loaded at 2 points, one big beam down there transferring load to 2 transverse ones. And you see a lot of people standing around. You're going to see them jump and run when they hear the first bang. That's because the test was not supposed to happen when it did the way it did. That was a mistake, an operator error in the lab, but we still recovered all of our data, and it was all very good data. Now I'm going to press play, and if you can see my cursor over here on the left where I'm pointing, you're going to see at the first bang a little puff there, and you're going to move over to the other side symmetrically, and you'll see a little bit of a failure there with a bang, and then back over to the left side, you'll see a complete failure. Okay, girder's going down. Failure, failure, and then complete failure, fracture of the FRP right through the web. So I'm going to play that one more time so everybody gets a chance to see it again. And there, the girder is completely failed. So what's happening here? Well, we're getting failure due to compression flange buckling. The compression flange itself is actually failing. And we had anticipated that this could happen. We had designed around it. And we did that using an analytical model that was published 23 years ago in the ASC Journal of Engineering Mechanics. It's a fairly complex model. I've just put a few equations up here to show you that, yeah, there's a lot going on in there. However, it's not that hard to implement. It's pretty tractable if you have the laminate properties of your compression flange and your webs that partially restrain it rotationally. And that model predicted buckling would occur at a compression flange stress of 157 MPa. If you just straight up take nominal properties of the girder and do a laminate analysis and input those properties in, it's 157. We computed FRP strains at that first failure of 152. And those computed strains are going to be quite accurate because remember, we also measure strains in the girder, in the bare girder cross section, and we can compare them with computed there. This section is essentially linearly elastic. MC over I does a very good job of telling us what's happening. So this is excellent agreement between what we actually saw and what we would have expected. We didn't anticipate buckling failure to occur because that wasn't predicted to be the first failure mode. We expected yielding of the reinforcing or perhaps failure of the concrete ridges, but it actually went to a much higher load than expected and it failed in buckling. To reinforce that, this is a plot of applied load versus strain in the tension reinforcing. So that's the reinforcing in the deck on the bottom. And we instrumented a lot of bars there. There were 5 bars instrumented in the top layer, 5 in the bottom layer. And you can see the plot here, very consistent strain readings. And the peak ones are up around 2,700 microstrains. One takeaway from this is the steel did not yield. Okay, if the steel had yielded, you would see a very large increase in strain with small increase in applied load. That's what happens with reinforced concrete sections once the steel starts to yield. And this is right at the centerline splice where it's just reinforced concrete. We don't see that. 2,700 microstrains also corresponds to a stress of just under 80 KSI. So we spec'd 60 KSI steel. We actually got a higher grade of rebar, and which is not unusual for the actual yield strength to be a good deal higher than the nominal value. And this is why the capacity of the specimen, one of the reasons why the capacity was so much higher than what we expected it to be. I want to give you a quick snapshot of what happened with the compression rebar strain data. We can look at more information here. We're looking at sections D and B and A, and D is the furthest out in the splice, furthest away from centerline pier. B is closer into the center line, and section A is right at the center line of the splice. And you can see that we are picking up significant compression in those compression rebars. That means there's significant compression in that concrete infill. And it's increasing as we move along the splice. And that's consistent with that shear stress transfer of the compression stress in the carbon fiber bottom flange or top as tested into the concrete itself. In other words, the load transfer, the stress transfer is happening as we assumed and expected it would. I'm not showing it, but we also have good strain data on the compression flange that also shows that stresses there are reducing as you move along the splice. They're moving into the concrete and away from the actual FRP girder. I want to close out just talking about the practical significance of this research, of that continuity joint. What does it actually do for us? I mentioned early on, motivation is, reduces live load deflections. It can increase design efficiency. What does that mean practically? Well, here we're comparing our model structure with two 50-foot spans and if it's continuous, giving us a 100-foot long structure, versus the case where it was two 50-foot simple spans. In other words, we don't have the continuity joint. And as designed as a continuous structure, the cross-section of the girder that we designed to meet deflection and stress requirements is shown on the left. It's 546 millimeters deep, so that's about 22 inches. And then there's another 8 inches of deck on top, a 25 millimeter bottom flange. Now, if we were to maintain that bottom flange thickness and design that as a 50-foot simple span, we would get the section shown in the middle. In other words, the depth of the girder would have to increase from 546 millimeters to 991. And that's a deflection-driven design. That's actually to meet a live load L/1000 deflection requirement that is specified by AASHTO for any bridge where you've got a sidewalk. And then if we allow the bottom flange thickness to increase up to the maximum practical value of 51 millimeters or 2 inches, that's about all you can infuse effectively, you would still have to increase the depth of that section for a simple span from 546 to 724. Again, it will be a deflection-driven design. So the benefits of that live load continuity are very clear. And this is, we're hopeful that this is going to open up new markets for the CT girder in its use in continuous structures. And the Stillwater Avenue Bridge is going to be the first test case of that. So in conclusion, I'll point out a few things. First of all, that splice performance exceeded our design requirements. We got well beyond what we expected. We did carry more shear stress in the ridges than we had anticipated as well. We can calculate that from our test results, and it shows that it does better than we expected. I'm confident that the design method can be improved to reduce some of that conservatism, and we know, I think, why it's a little bit conservative. Compression flange buckling, that did occur, and that has to be accounted for in design. It's another limit state you've got to look at. The good news is we can rationally do that with existing models. The experiments agree very well with what they predict. All our measured strains supported our assumed load transfer mechanisms. The practical benefits of continuity are potentially very significant. And at the end of the day, we can be very confident in the performance of the continuity joints in the Stillwater Avenue bridges. And I was very happy when this test was completed successfully because we actually designed those continuity joints and the girders had been fabricated and were all spec'd out before we actually tested the continuity joints. So I'm really glad that the test supported the design of those bridges. I will say that with Stillwater, those girders are actually sized as if they were simple spans. So we are not taking full advantage of that continuity. It will definitely give that bridge some real benefits in terms of performance, longevity through elimination of joints and things of that nature. That's going to be very helpful. But structurally, for this first test case going out there, or I should say case is, because there are two bridges, we are not actually relying on those joints. We will be instrumenting that bridge heavily and monitoring it over a period of time. That work is going to be starting up basically as soon as that bridge is in place, and we're already working towards getting the instrumentation installed right now. So a lot more will come over the next few years from that. All right, thank you for your time. Again, I apologize for not being able to be there and answer your questions and connect with you. I always enjoy coming to this conference, but some other travel was already booked, and that simply could not be changed. Thanks again. Bye.